Okay, so this is lab 3, circuits. So the purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel, and to use multimeters to measure conventional current and potential difference, and to examine the behavior of ohmic resistors and capacitors. And so the big physical concepts we used here were conservation of charge and energy, which are exactly what they sound like. In a closed system, charge is conserved, energy is conserved. I spelled rule wrong, but the node rule and the loop rule. And so the node rule says that the current coming into a node is equal to the current coming out of a node. And the loop rule says that the potential across a closed circuit is 0. And so the results were that for the most part, our circuits behaved in a way that was consistent with what we predicted based on these rules. So this was the setup that we used to build our circuit. And based off of this setup, this is an in-series circuit, and so the current is consistent throughout the whole thing. And so the current is equal at the first ammeter to the current at the second ammeter. And so using this equation, we calculated that the theoretical current should be 0.02 amps. And so this is the circuit that we built, and we ended up measuring a current of 0.02 amps, which is what we predicted. And when we reversed the current, we also measured 0.02 amps because that doesn't change. And so then once we replaced one of the ammeters with a voltmeter, the second ammeter had a reading of 0 amps. And this is expected because the voltmeter has really high resistance, so the current couldn't travel anymore. And our voltmeter measured 3.1 volts, which we would expect it to be 3 because that's the potential difference across the battery. And so this is likely just measurement error. So we measured the potential difference across the different elements, and across the battery it was 3 volts, which makes sense because each of these batteries was 1.5 volts. And then across the 47 ohm resistor, we measured negative 0.9 volts, the second resistor negative 2 volts. And so theoretically, these should all sum up to 0 because of that loop rule conservation of energy, that the potential across a closed circuit should sum up to 0. Our actual sum was 0.1 volts, and we attributed this error to the fact that there could be resistance in the wires. And so this is what the potential graph should look like across this circuit. The potential increases across the battery and then decreases at each resistor with the slope proportional to the amount of resistance. And the reason that the ammeter readings didn't change when we attached the voltmeter to measure these potentials is because the voltmeter has very high resistance, and so almost none of that current is actually going through the voltmeter. It's just staying the way that we had it set up. And then when we attach an ammeter in parallel across the 100 ohm resistor, we anticipate that the current would pass through the ammeter instead of the resistor because the ammeter has a lower resistance. And so this would cause a decrease in resistance and an increase in current, and the predicted current based on this is the same as the current that we observed. So then we calculated all of the resistances based off our experimental data, and these lined up pretty much with the expected values with some resistance in the wire. And so then this was our RC current. We charged a capacitor, and you could see the light bulb charging as the capacitor charged. And so then based off of the charging times, we were able to generate this plot of the natural log of the voltage versus time. And if we charged the capacitor with no resistor, the capacitor would charge instantly, And if we used an actual ammeter, there would be more resistance in the ammeter, which would change the current readings slightly.